Hi friends, welcome to our YouTube channel Knowledge Academy. The main aim of this playlist is to teach or discuss the previous year gate questions of all subjects in a very detailed manner. If you are seeing this video for the first time in this channel, then please go back to the playlist gate previous year questions and see the lectures from the starting so that the lectures will be understood in an easy manner and the concepts will be understood in a very clear manner. If you like the content of this lecture, then please do like, share and subscribe our channel and don't forget to press the bell icon button. So whenever we upload a video, the direct notifications will come directly to your mobile phone. The main aim of this lecture is to teach you or discuss the 10 important questions of network theory, which are the previous year gate questions. So let's get started. So now we will move forward to solve the question number 71. In this question, this is a circuit which is all the resistor in this except this resistor, all the values of the remaining resistor have a resistance of 1 ohm and this resistance has a value which is 2 ohm, and there is a voltage source, ideal voltage source, which has a voltage of 8 volt, and we need to figure the current in this 2 ohm branch. The main aim of this numerical is to figure out the current in the 2 ohm resistor, and this question is given in the gate 2015 year for the 1 mark. So now let's get started to solve this numerical. See here, there are actually, we need to figure out how many nodes are there in this circuit. If you see carefully, there is a node, let me assume it has symbol A, and similarly there is another node, let me assume it has B, and similarly here at this particular node 3 branches are coming to contact. So let me mark this as a C node. And here also there are 3 branches are incoming, are contacting. They are connected to a particular junction. So let me denote this junction as a D. So if you see carefully, there are actually 4 nodes. So I am going to redraw this circuit so that it is easy for us to know which type of circuit is this. So I am going to redraw the circuit. This I am taking it as a node A. And similarly here I am taking it as a node B. And here it is A and it is B. I am marking it here it is a D, and here I am marking it as a D, node C. So there are total 4 nodes A, B, C, D. See, between A to D there is a 1 ohm resistor. There is a 1 ohm resistor, right? 1 to D. So it's not finished. From D to C there is a 2 ohm resistor. There is a 2 ohm resistor. So from C to B there is a resistance of 1 ohm. There is a, from C to B there is a resistance of 1 ohm. So this is 1 ohm. And similarly between A to C there is a resistance of 1 ohm. So this is also 1 ohm. And the remaining thing is D to B. D to B there is a resistance of 1 ohm. There is a resistance of 1 ohm. So there are actually 5 resistors and 5 resistors are connected. So this is an equivalent circuit, and between A and B there is a voltage source of 8 volt. So we need to connect a voltage source which is 8 volt, which is actually 8 volt. A is positive and B is negative. So I have connected in certain fashion that A is negative, positive and B is negative. So this is 8 volt. We need, the current is traveling from D to C. So I must keep a current which is traveling from D to C in this equivalent circuit. So I have drawn in such a fashion so that these 2 circuits are equal, and we have to figure the current in this 2 ohm resistance. If you see carefully, this circuit is a balanced resistance bridge, because here let me consider this as Z1 and this resistance as Z2 and this resistance as Z3 and this resistance as Z4. If you see carefully, here Z1 into Z4 is equal to Z2 into Z3. This condition is satisfied by this circuit. Means Z1 is 1, Z4 is 1, Z2 is 1 and Z3 is 1. So 1 is equal to 1. This circuit is satisfying this balanced resistance bridge condition. So in that condition, at that particular condition, the current in this branch is equal to 0. Means the current in the 2 ohm resistor is 0. Means no matter what you count, no matter what the amount of resistance you connect, when the circuit is satisfying the balanced resistance bridge, no matter what resistance or reactance or capacitance you connected across this branch B and D and C, always irrespective of the resistance, irrespective of the impedance, the current in the branch is always zero under the balanced Wheatstone condition. So therefore our final answer is I is equal to 0 ampere. So now let's move forward to do the other numerical. The question number is 72. In this question, there are three AC sources. The first AC source is connected to a capacitor of reactance minus J1 ohm, and the second AC source is connected to an inductor of reactance J1 ohm, and the third AC source is not connected to any resistor or impedance. It is directly connected to the circuit. So here the main aim is to figure out the value of the current in this third AC source. The current which passing through this source we need to figure out. When V1 is 100 angle 0 and V2 is 100 angle minus 120 degree and the V3 is 100 angle plus 120 degree. This question is given in the GATE 2015 year for 2 marks. See here, there are actually V1, V2, V3. Their magnitudes are equal and they are displaced by an angle of 120. Means a 3-phase balanced supply is given. Is given in the circuit. So we need to figure out the value of the current in this circuit. So if you see carefully, there are actually 2 nodes. This is the first node and this is the second node. This is node 1 and this is node 2. So out of these 2 nodes, by nodal analysis method, I am going to solve this example, this numerical. So out of these 2 nodes, I am going to assume one node as a reference node. Means the reference node I am going to assume the potential across the reference node is 0 and the other node voltage we must figure out. So here I am assuming this as a 0 potential, means reference node. So this node potential, let me assume it is Vx. If you see carefully, this is 0 volt and this is Vx. So Vx is higher potential than the 0, the reference node. So therefore Vx minus 0. Vx minus 0 is equal to the potential difference is the voltage of the AC source, which is the third one. So therefore V3. So therefore Vx is equal to V3. So out of 2 nodes, one node reference node we have taken, its potential is 0 and the another node voltage which is equal to the supply voltage of the third source, which is V3. So now by nodal analysis method. So now we will do by nodal analysis method. NAM means nodal analysis method. By nodal analysis method, let me assume the current, the direction of the current is already given into the node. So by nodal analysis, all the currents leaving at a particular junction, the sum of all the currents leaving at a particular junction is 0. So I am assuming the current is leaving in this branch, and in this branch also I am leaving. So if you calculate from here, this is Vx and this is 0, right? But here the potential is plus V1. So therefore the current is in this branch Vx minus V1, Vx minus V1. Vx is V3, right? So Vx is V3. I am writing directly it is Vx is equal to V3. So V3 minus V1 by minus J1. Reactance is minus J1. So plus Vx is equal to V3, right? So I am writing it here. Vx is equal to V3. So therefore the current in this branch is Vx minus V2 by J1. So V3 minus V2 by J1. And similarly, the current, here I am assuming the current is leaving the node, but actually the current is incoming. So incoming, if it is positive, then the outgoing has to be the negative of L. So therefore minus A is equal to 0. So now we know the value of V3, we know the value of V1, and we know the value of V2. All these things we know, V1, V2, V3. In this equation only one parameter is there, which is unknown, and the remaining all parameters are known. So by substituting all those values and after doing simplification, we will get answer I is equal to 173.2 at an angle of minus 60 degree. This is our required solution. Therefore, the current I is equal to 173.2 at an angle of minus 60 degree. After solving the previous problem, now let's move forward to do the another numerical. The numerical number is 73. In this question, there are actually two electrical circuits. In the first electrical circuit, there is a 2 ohm resistor and 1 ohm resistor. And the same thing repeats again, 2 ohm, 1 ohm. And similarly, 2 ohm, 1 ohm. The circuit goes on repetition up to infinity. Similarly, in the second resistor circuit, there is a 1 ohm. And again 2 ohm, 1 ohm, the same repetition occurs. 2 ohm, 1 ohm, again 2 ohm, 1 ohm, again 2 ohm, 1 ohm, and the same thing repetition occurs up to infinity. So the main aim of this numerical is to find the relation between RA and RB. Means the first circuit effective resistance and the second circuit effective resistance. We need to find an equivalent. We need to find a relation between RA and RB. This is our main aim in this numerical, and this numerical is given in the year 2016 for the 1 mark. So now let's get started to solve this numerical. If you see carefully, there is actually 2 ohm, 1 ohm, 2 ohm, 1 ohm, again 2 ohm, 1 ohm. Same thing repetition. You see carefully here, this circuit is also same. 2 ohm, 1 ohm, 2 ohm, 1 ohm, 2 ohm, 1 ohm, and the same thing repetition occurs. So therefore, this RV, this is equivalent. This total circuit is just the effective resistance of RA. Means from here, the effective resistance from here. If you see carefully, the effective resistance of all this circuit is RA. So therefore, I am going to rub all this crazy circuit, so that now I am going to rub all this crazy circuit, because the effective resistance of this part of the circuit, which is already given in the previous first circuit, that equivalent resistance which is already given, which is the resistance which is RA. So therefore, this whole circuit resistance is RA. So therefore, this is a resistance RA, equivalent resistance is RA. So now 1 ohm and the RA are in parallel each other. So therefore, RB is equal to 1 into RA by 1 plus RA, because they are a parallel combination. Therefore, answer is RA by 1 plus RA. So now we figure out the relation between RA and RB. So therefore, RB is equal to RA by 1 plus RA. This is the required solution of this numerical. After solving the previous problem, now let's move forward to do the another numerical. The numerical number is 74. In this numerical, there is a parallel branch. In the first branch, there is a 5 ohm resistor, and the second branch, there is a 2 resistors which are connected in series fashion, which is 4 ohm and 6 ohm. So in these questions, they are given that the power absorbed, the resistor will always absorb the power. So therefore, the power absorbed by the 5 ohm resistor is 10 calories per second. Means the power which is absorbed by the 5 ohm resistor is given that 10 calories per second. And we need to figure out, in this question, the main aim is to figure out the power absorbed by the 4 ohm resistor is how much in calories per second. This question is given in the GATE year 2016 for 1 mark. If you see carefully, energy is equal to power into time. So in SI system, the unit of the energy is joules, and power is watt. The SI unit of power is watt, and the time is second. So therefore, wattage is equal to joules per second in SI system. Means I am trying to say the unit of power is watt or joules per second, and there is also another unit in another system which is calories per second. So the unit of power can be wattage or joules per second or calories per second. These 3 units are valid units of the power. So in this question, we need to figure out what is the power absorbed by the 4 ohms in the circuit. If you see carefully, we need to find the current in the 4 ohm resistor. Then only we can find the power absorbed by the 4 ohm resistor. Let me assume the current in this branch is I. The current in the first branch is I. Let me assume like that. And let me also assume there is a voltage difference across the 5 ohm resistor. Means this voltage is in parallel, the voltage across 5 ohm is also equal to the voltage across the combination of 4 ohm and 6 ohm. So they have already given power is equal to in the 5 ohm resistor is 10 calories per second. So therefore the power absorbed by the 5 ohm is equal to voltage across the V square by R. I am trying to use the equation V square by R. V is the voltage across the 5 ohm, which is V square by R. R is the resistance, which is 5. Power across 5 ohm is already given, which is 10 calories per second. So V square by 5 is equal to 50. So we need V. V is equal to root over 50. So the voltage difference, the voltage across the 5 ohm resistor is root 50 volts. So now we need to find the current in the 4 ohm resistor. See, this voltage is same across 5 ohm and the combination of 4 ohm and 6 ohm. As the 4 ohm and 6 ohm are in series, so therefore the net resistance is 4 ohm plus 6 ohm is equal to 10. So this equivalent resistance is total 10 ohm. Therefore, the current is, voltage is V, current is I, and the total resistor is 10. So therefore, V is equal to IR. V is equal to I, and the R is 4 plus 6. But V is already we know, root 50, right? Root 50. And the current we need to figure out. Therefore, 4 plus 6 is equal to 10. So now, if you do calculation, I is equal to root 50 by 10. This is the ampere. This is the ampere which is going through the combination of series combination of 4 ohm and the 6 ohm. We need to find the power absorbed by the 4 ohm. So therefore, power absorbed by the 4 ohm is equal to current in the 4 ohm. Current in the 4 ohm is I. So therefore, I square R. I square into R is how much? 4. So 4I square means 4I square we can write. But we already know the value of I, root 50 by 10. So therefore, 4 into root 50 by 10 whole square. Now if you do the simplification, we will get power absorbed. If you do the simplification, finally we will get power absorbed by the 4 ohm resistor is 2 calories per second. 2 calories per second. So this is our solution. So therefore the answer is 2 calories. The power absorbed by the 5 ohm resistor is 10 calories per second. Then the power absorbed by the 4 ohm resistor is 2 calories per second. After solving the previous problem, now let's move forward to do the another numerical. The numerical number is 75. In the circuit, there is an ideal voltage source which has a voltage of 1 volt, and there are three identical resistors of 1 ohm, and there is a dependent current source. The dependent current source this is a dependent current source. The value of this current source depend upon the current flowing in this branch, which is I2. And there is a current I1 passes through this 1 volt. And our main aim in this question is to figure out the value of the current I1. This question is given in the GATE year 2016 for 1 mark. So now let's get started to solve this numerical. If you see carefully, there are two nodes, node 1 and node 2. See, by KCL, the current incoming to this node is I1, and there are two currents which are coming outside of this node. So by KCL, sum of incoming currents is equal to sum of outgoing currents. So there is only one current which is incoming. So by KCL, the sum of incoming currents is equal to sum of outgoing currents. So there is only one current which is incoming to the junction, and there are two currents which are passing outside of the junction. So the incoming current is only I1, so therefore incoming current is equal to sum of outgoing currents. So outgoing currents are two currents which are I2 and plus I2. So therefore I1 is equal to 2I2. So I will take this 2I2 to the left side. Therefore I1 minus 2I2 is equal to 0. This is the first equation. This is the equation number 1. And if you see carefully, the current is always travels from higher potential to lower potential. And similarly, in this also the current travels from higher potential to lower potential, and in this also current travels from higher potential to lower potential. I am going to make a KVL in this loop. I am going to make a KVL in this loop. Therefore, by KVL, the arithmetic sum of or algebraic sum of voltages in a closed loop is equal to 0. So therefore, minus to plus, there is a rise in voltage, just plus 1. And from plus to minus, there is a drop in potential. So therefore, minus 1 into I1, the current and the voltage, and the current and the resistor. And up from here, plus to minus, again there is a drop in potential. So therefore, minus I into 1 into I2. And from here, plus to minus, again there is a drop in potential. So therefore, minus 1 into I2. So their closed sum is equal to 0 because we found a total closed loop. So therefore, it is equal to 0. So therefore, 1 minus I1 minus I2 is equal to 0. So therefore, 1 minus I1 minus 2I2 is equal to 0. Now I am going to multiply minus 1. Therefore, on both sides. Therefore, it will become I1 plus 2I2. Then minus 1 is equal to 0, right? So I will take the 1 to the other side. So therefore, I1 plus 2I2 is equal to 1. This is the second equation. If you see carefully, this is the first equation and this is the second equation. There are two equations with two unknowns, which are I1 and I2. So by solving these two equations, finally we will get I1 is equal to 1 by 2 ampere and I2 is equal to 1 by 4 ampere. So therefore, we need only the current I1 which is asked in the question. So therefore, I1 is equal to 0.5 ampere. So therefore the current through this 1 volt is 0.5 ampere, which is the required solution. So after solving the previous problem, now let's move forward to do the another numerical, the numerical number 76. In this question, there is a voltage source which has an expression V of t is equal to 100 plus 10 sin omega t minus 5 sin 3 omega t. To measure this voltage, we have connected a voltmeter. In these two voltmeters are used. The first voltmeter is moving coil voltmeter. Means if we connect a moving coil voltmeter across the voltage source V of t, it has read a voltage of V1. I am repeating it here. So when we connect a moving coil voltmeter across the V of t source, we got a voltage read which is read by the voltmeter is V1. So in the next case, we have connected a moving iron voltmeter to measure the voltage source V of t. Then we got a reading by this moving iron voltmeter is V2. So our main aim in this question is to figure out the difference V2 minus V1. V2 is the voltage which is read by the moving iron voltmeter and V1 is the voltage measured by the moving coil voltmeter. So this question is given in the GATE 2016 for 2 marks. So now let's get started to solve this numerical. If you study the measurement subject, you will get to know that moving coil voltmeter always reads the average value. The moving coil voltmeter always reads the average value. And the moving iron voltmeter always reads RMS value. This I am going to explain in my channel in measurement subject. In a very short span of time, I am going to take lectures on each subject in different playlist. Up to that time, please remember these things, that moving coil voltmeter is going to read only the average value of the voltage, and the moving iron voltmeter is going to read only the RMS value of the voltage. So therefore, this is the voltage, right? So we need to figure out the average value of the voltage. So V of t, we need to find the average value. We need to find the average of the V of t. So therefore, average of sin omega t. Sin omega is the pure sinusoidal waveform. Therefore, it is symmetrical about the x-axis. Therefore, it has some positive and a negative. So their net effect is 0. Therefore, sin omega t and sin 3 omega t, their net averages becomes 0. So therefore, only DC component will have a non-zero DC value, non-zero average value. So therefore, these two, the average value of sin omega t and the average value of sin 3 omega t is becomes 0. So therefore, only one number is present in the expression, which is 100. Therefore, the average value of the V of t is 100. And similarly, if we do the RMS value of V of t, so RMS value of the V of t is equal to RMS value of V of t. It is root over RMS of the first one. RMS of the DC value is same itself only. So square, we need to do the square, 100 square. RMS value of the first whole square plus RMS of the second square. RMS of 10 sin omega t is Vm by root 2. Vm is 10. So 10 by root 2 whole square. 10 by root 2 whole square. And similarly, the RMS value of the third expression is 5 sin 3 omega t. So therefore, 5 by root 2 whole square. 5 by root 2 whole square. So if we do a simplification of this equation, finally we will get is equal to 100.312 volt. This is 100 volt and this is 100.312 volt. So the average, the moving coil voltmeter reads the average value. So therefore this is the average value, right? So this is going to be the V1. And similarly, moving iron voltmeter is going to read the RMS value. So therefore this is the RMS value. Therefore this is the V2. So our aim is to find the V2 minus V1. So 100.312 minus 100 is going to be 0.312 volt. So this is the required solution of this numerical. So just remember two things. Moving coil voltmeter reads only the average value, and the moving iron voltmeter reads only the RMS value of the supply. So after solving the previous numerical, we will move forward to do the another numerical. The numerical number is 77. In this numerical, they have given a ideal current source of 5 ampere and there is a resistance of 5 ohm, and in this branch there is a combination of 5 ohm resistance and a dependent current source of 10 I1. The I1 is flowing in this branch, which is a 5 ohm, and there is a ideal voltage of 10 volt. The aim of this circuit is to find the node voltage VA. We need to find the node voltage across this junction, across this node A. And this question is given in the gate for 2 marks in the year 2016 for given 2 marks. Now let's solve this numerical. See, there are 2 nodes in this circuit. There are 2 nodes. This is the node 1 and this is the node 2. In this node 1, let me assume the node 1 has a reference node. So therefore, this is going to be the 0 voltage. So there is a node A. At this node A, I am assuming the potential as VA. The node voltage has a voltage which is VA. I have represented VA. So we need to find VA, right? Which is the exact value which we need to find in this example. So therefore, by nodal analysis method, NAM means by nodal analysis method, the algebraic sum of currents which are leaving at a particular junction is equal to 0. So let I assume that all the currents are leaving. Let me assume all these currents are leaving. All the currents are leaving the junction or node A. So therefore, the current in the 5 ohm is VA minus 0 by 5 plus, and the current in the current source is which is current going inside the junction, but we need the current which is going out of the junction, so it will be minus 5. So then we have to write plus. If you see carefully here, we need to write expression for the current which is leaving the junction. So therefore, VA minus of, if this is the 0 potential, then this potential will become minus 10I because there is a negative upward, that's why it will become minus 10i. See, I'm going to tell you small concept. Suppose if you are confused whether to take it as a minus or plus, let me tell you a small concept. Suppose this is V1, right? Let me assume this voltage is suppose 5 volt. Let me assume this is a 5 volt, right? If I assume this is a reference node, then this node Vx will be how much? Whether it is plus 5 or whether it is minus 5. This we will going to figure out. See here, this is given higher potential. This is a low potential. Therefore, higher potential minus lower potential is equal to 5 volt. Higher potential is how much? Vx. Minus lower potential is 0. Is equal to, which is already given, just 5. So therefore, Vx is equal to 5 volt. So therefore, Vx is equal to 5 volt. Similarly, in the other case, suppose if you do and the reverse, suppose if there is minus and there is plus. Now they are given this as 5 volt. If this is a taken as a reference, now I need to find whether Vx is plus 5 or whether Vx is minus 5. So here, this is positive, right? And this is negative, right? So therefore, higher potential is 0 now. 0. Lower potential is minus Vx. So 0 minus Vx is equal to 5. Therefore, Vx is equal to minus 5. So what I am trying to say is, if it is minus, directly write minus 5. If it is positive in the upward, then take Vx is plus 5. So in the same pattern, applies in this concept also. I tried to tell the concept behind taking it as minus or positive. So Va minus of, if I take this as 0, so therefore this node potential is going to be minus 10i. So Va minus of minus 10i by resistor is 5 plus this branch is finished, this branch is finished, and this branch is finished. So only the remaining branch is this branch, last branch. Therefore Va minus 10 by 10 ohms. So Va minus 10 by 10 ohm is equal to 0. This is the algebraic sum of all currents leaving a junction is equal to 0. So if you do the simplification, let me take the LCM as 10, because 5, 5, 10 is LCM is 10. So I have to make it as a multiplication with respect to 10, 2, right? So 2 Va, and this is 10, right? 10 into 5 minus 50, and I need to multiply with 2. LCM is 10, right? So 5 2 is a 10, so it will become 2A. So 2A minus 2 minus plus, so plus 10 into 2 plus become 20, plus 20 I1 plus, here the LCM is 10, so nothing we have to multiply. So therefore Va minus 10, so the total LCM is 10. Total LCM is 10 is equal to 0. So if it goes to the right side, it will become 0 again. So now I have to write this LCM. I am going to rub it here itself only, so that I can easily do the calculation. If you do 2A and 2A and 2A, there are, so 2A plus 2A, 4A plus VA, 5VA. 5VA. This is finished, and this is finished. 20 I1 plus 20 I1 plus 20 I1, and the remaining things are minus 50 and minus 10. So it will become minus 60. So if I take it to the right side, it will become plus 60. So this is the first equation. This is our first equation. Now see, if you see, I1 is equal to Va higher potential minus 10 by 10. So therefore I1 is equal to Va minus 10 by 10. I1 is equal to node potential Va minus 10 by 10 ohm. So if you do the simplification, it will become 10 I1 is equal to Va minus 10, right? So therefore Va, if I take 10 I1 to the right side, Va minus 10 I1, if I take 10 ampere to the left side, it will become 10. This is the second equation. If you see carefully, we have two equations and two unknown parameters, which are Va and I1. If you do the simplification with two equations with two unknowns, after solving the equations, we finally get VA. We get VA is equal to 11.42 volts. We get VA is equal to 11.42 volt, and the current I, and the current I1 is equal to 0.142. So therefore current is equal to 0.142 ampere, and the voltage VA is equal to 11.42 volt. So therefore VA is equal to 11.42 volt. This is our required solution. After solving the previous problem, now let's move forward to do the another numerical, the numerical number 78. In this question, they have given a voltage. Actually, there is a load which is denoted by a symbol Z. Across this load, there is a voltage expression V of t, and there is a current passing through this load, which is I of t. So the voltage across the load is V of t, and the current through the load is I of t. They have given the expressions for V of t and I of t. The expressions for V of t is equal to 100 sin omega t, and the expression for the current is I of t is equal to 10 sin omega t minus 60 degree plus 2 sin 3 omega t plus 5 sin 5 omega t. So the aim of this question is to figure out the average power which is consumed by this load. We need to find the average power which is consumed by this load for this voltage and current relation, for their expressions. So this question is given in the year 2016 for 1 mark. So if you see carefully, suppose we need first to solve these problems, we need to know first basic formulas, and these formulas I am going to explain in my theory classes which are going to come in coming few days. So until that time, remember these formulas, so that it is very useful to solve in any competitive examinations if this type of numericals are come in any examinations like competitive examinations. If say here V of t is equal to Vm1 sin omega 1t plus Vm2 sin omega 2t and so on. And similarly I of t is equal to Im1 sin omega 1t plus phi 1 plus Im2 sin of omega 2t plus phi 2 and so on. Then the P average. Then the P average is we will get the average power consumed by the load. P average is equal to RMS quantity of the first signal, which is Vm1 by root 2, and the RMS of this current expression, this expression Im by root 2, and the phase difference between these two vectors, which is cos of phi 1. Phi 1 is the phase difference between these two signals, only these two signals. Similarly, the RMS value of the second signal, which is voltage Vm2 by root 2, and the RMS of the second signal is Im2 by root 2, and the phase difference between this signal and this signal is phi 2. So we need to multiply with cos and so on. Then only we can figure out the average power consumed by the load. So now with this basic formula, we will try to find the average power which is consumed by the load. So therefore P average is equal to, if you see carefully, there is only sin omega t and sin omega t. There is no terms like sin 3 omega t in the and sin 5 omega t. There are no expressions in like sin 3 omega t and sin 5 omega t. So we can easily assume like 0 into sin 3 omega t plus 0 into sin 5 omega t. I can write like this. So anyhow it will become finally 100 sin omega t. So by using this formula, see here 100 by root 2. So 100 by root 2 RMS of first signal into this is 10 by root 2 RMS. Between these two signals, phase difference is only 60 degrees. So cos of 60 degrees, right? Cos of 60 degrees plus here it is 0. 0 by root 2 is again 0. So 0 into 2 by root 2 into cos of 0 is again 0. So everything is 0 and anything is 0 plus here RMS is 0 by root 2. So again 0. 0 into everything is again 0. So therefore only this expression is going to be valid. So remaining all these terms are 0. So now we need to write this one. Cos 60 is 1 by 2. Cos 60 is 1 by 2. If you do the calculations, you will get answer is equal to 250 watt. So the average power which consumed by the load is 250 watt. Suppose, see here, I am going to write just 250 watt. Suppose in the question they have asked like this. Suppose we need to find the power factor of the load. Suppose we need to find the power factor of the load. Suppose in the question they are asking to find the power factor of the load. Then P average is equal to VRMS, IRMS and the cos phi. P average is already known, just 250. And VRMS is we need to find the RMS value of this voltage across the load, which is 100 sin omega t. So RMS value is 100 by root 2. 100 by root 2 is the RMS value. And we need to find the RMS value of the current which is drawn by the load. So we have known which is root over 10 by root 2 whole square, because RMS of the first signal is 10 by root 2 whole square plus, and this is RMS is 2 by root 2, 2 by root 2 whole square plus, and here is 5 by root 2, right? 5 by root 2 whole square. This is the net RMS of the current in the load. And finally we need to write the into cos phi. If you see carefully, in this whole equation only cos phi is the unknown. So by solving we can easily figure out the value of the cos phi. So this is the power factor of the load. This is the power factor of load. So by this we can easily figure out the power factor of the load. I didn't calculate the value. Please try calculate this value in your notebook and write it with your calculator and write this answer in your notebook. So with this example we learned two concepts. We have figured out the average power consumed by the load and also the power factor of the load. After solving the previous problem, now let's move forward to do the another numerical, the numerical number 79. In this numerical, there is a voltage source which is ideal voltage source of 10 volt and there is a resistance of 2 ohm and another ideal current source of 5 ampere is connected in this fashion. The aim of this question is to find the voltage across the ideal current source, which we need to find. This is the V1 is equal to we need to find, which is the voltage across the ideal current source. This question is given in the GATE 2016 for 1 mark. So now let's get started. And this is the very easiest problem, but even then we will solve it. So it is given in the GATE 2016 for 1 mark. So let's get started. Say here, if you see carefully, the current in the current source it is given as a 5 ampere. So therefore the direction of the current is also given from down to up. So therefore in this branch the current is 5 ampere. Similarly in this branch is also the current is 5 ampere. So therefore in this branch also current is 5 ampere. And the current always travels from higher potential to lower potential. So the current is traveling from here to here. So therefore this is higher potential and this is lower potential. So I am making a KVL in this loop like this. KVL. So I am traveling from this direction minus to plus. So therefore by KVL the arithmetic sum of voltage drops in a closed loop is equal to 0. Therefore minus to plus. So therefore is a rising potential which is plus 10. And after traveling up to here again I am going from negative to positive. So therefore rising potential. So therefore plus current is 5 ampere and the resistor is 2. Current into resistor law. So from up to traveling from here, I am traveling from plus to negative. Again there is a drop in potential minus V1. Minus V1 is equal to 0. So 10 plus 10 minus V1 is equal to 0. So if you solve this equation, finally we will get V1 is equal to 20 volt. Means the voltage drop across the ideal current source is 20 volt. So therefore we figured out the value of the V1 which is 20 volt. This problem is the last question in this lecture. and the problem number is 18, and this is the most easiest problem. This question, it is a circuit. In this, the resistance are connected in this fashion, which is 1 ohm, 3 ohm, 0.8 ohm, 2 ohm, 6 ohm, 3 ohm, 6 ohm, 1 ohm and 1 ohm. All these resistance are connected in this fashion. And this question is given in the GATE 2017 for 1 mark. And this is the most easiest sum. And we need to find the R equivalent. Means the equivalent resistance when we see across these terminals. This we need to figure out in this question. See here, I can redraw this circuit in this fashion. So here, if you see carefully, here I am writing here 1 ohm, and here it is 0.8 ohm. This is 0.8 ohm, 0.8 ohm, and this is 1 ohm. If you see, this is a 3 ohm, right? This is 3 ohm. This is 3 ohm. If you see here, this is 6 ohm, just connected from here to here. So I can make it come up to this point, because this node and this node is common, same node. So I am going to write here this as a 6 ohm. And similarly here there is a 2 ohm resistance. And see, this is a 6 ohm. This is a 6 ohm. It's connecting this node and this node. So this is a 6 ohm resistance. And similarly, the 3 ohm resistance is connected from here to here, because this node and this node is same. So I am writing it here, which is 3 ohm. And finally, 1 plus 1, because they are connected in series fashion, it will become 2 ohm. So it will become 2 ohm. So now 3 parallel 6 means 3 parallel 6 means 3 into 6 by 3 plus 6. It will become 2 ohm. So therefore the equivalent is 2 ohm. So I am going to replace this circuit, this equivalent by one simple resistor, which is 2 ohm. Similarly, here also 3 parallel 6. So again this will become a 2 ohm. I am replacing this circuit, this equivalent by 2 ohm. And 2 parallel 2 is again 1 ohm. So therefore, I am replacing this whole circuit by one resistor which has a value of 1 ohm. And 2 ohm and 1 ohm are in series connection. Therefore, 2 plus 1 is equal to 3 ohm. So I am going to replace by equivalent circuit which has a resistance of 3 ohm. Again, if you see, 2 and 3 are in parallel. So therefore, 1 plus 1 and 0.8 are in series. Therefore, R equivalent is equal to 1 plus 2 parallel 3 means 2 into 3, 6, 2 plus 3, 5, plus 0.8. So if you do 0.8, if you do the simplification, finally R equivalent is equal to 3 ohm. This is our required solution. So therefore R equivalent is equal to 3 ohm. This is our final solution. Successfully, we have completed 18 numericals by this lecture, and we will solve more and more numericals of previous year GATE questions of network theory in the coming days. And also we will solve each and every subject numericals in the same fashion as we are dealing right now. So if you like the content of this lecture, then please do like, share and subscribe our channel, and don't forget to press the bell icon button. So whenever we upload a new video, the direct notifications come to your mobile. In this COVID-19, stay home and stay safe. If any improvements needed in our lecture making and in our content of the lectures and the way of teaching style, then please do provide comment in our comment section, and we will read each one comments. Up to now, so many of them have messaged and they have commented in the comment section. We have read all the comments, and we will do all our best to improve all these things which you have told in the coming days. All these cannot be done simultaneously at one time, so we will take one after the another, and we will improve ourselves in video making process. So up to that time, have the lectures and see them and enjoy the lectures and enjoy the content of these lectures. Thank you so much for watching these videos.